Hello, everyone, and welcome to today's webinar. My name is Zuzana, and I'm happy to introduce our topic today, which is the final event of our SCORES project, Hybrid Domestic Energy Systems of the Future. This webinar is organized by European-funded project SCORES, co-organized with the BUP, and kindly joined by our cluster project, HyBuild. A recorded version of this webinar will be available. So feel free to follow the project website at scores-project.eu and our profiles on Twitter and LinkedIn, where we post regularly. We'd love to hear from you during this event. There is a question function in the tool. Please share your questions and any comments during the event, anytime during the event. We have a Q&A session planned right after the presentation of the technologies of the SCORES project. Now I'd like to introduce today's first presenter, Pavel Bodiš. He's a systems integrator at TNO and technical coordinator of the SCORES project. Pavel will introduce the topic and the SCORES project to all of you. Pavel, the floor is yours.
Thank you very much, Susanna, for a nice introduction. And I would like to also welcome all of you who are listening and looking at our final SCORES event. As clearly from the title, this event is about SCORES project, and the SCORES project is a European Horizon 2020 project that is focusing on combining and optimizing energy generation, consumption, and conversion of renewable energy storage system, which is connected to various kinds of grids. Effectively, what we try to do, we try to combine various storage and conversion technologies in buildings, and we try to connect them via a building energy management system that should make smart choices about how the energy locally produced should be also locally consumed, so that the energy grids are as little as possible used in the system, and thus less and less expenses to be made in order to maintain and build those energy grids. Obviously, reliable operations and positive business case are essential towards our results, as only then we can apply this technology towards wider range of buildings. The project started about four years ago and has 12 partners, 9 work packages, and a budget from the European Commission of subsidy of about 6 million euros. That has gone too far. In principle, as I mentioned, we're looking at using the renewable energy generated in the building to be used directly by the building itself, and for that we have to deal with the unpredictability of the energy supply from the renewable solar energy sources. And we use various kinds of storage systems. That is why hybrid storage system, in order to buffer that energy and use it at the right moment in time when the demand is there. On the demand side, we obviously have the typical story of every building: electricity use, domestic auto use, space heating, as well as in this case refeeding the energy back to the grids. When I zoom in a little bit towards the partners that are involved in the project, we have the several research institutes, namely TNO from the Netherlands, IE Intec from Austria, but we also have quite a number of large or small, medium-sized companies, among others, non-Siemens, EDF, RINA, Stadtwerke Gleisdorf, etc. Each of those companies brings in specific know-how or technology to the project that is heavily used towards our system solutions. Objectives of our project have been already mentioned, but in principle, we are looking at targeting the increased self-consumption of the energy in the built environment, in buildings, and minimizing the impacts of the locally generated renewable energies towards the grids. More specifically towards technologies, we are applying second life lithium-ion batteries coming from buses, We are also applying in our systems optimized electrically driven heating system on the basis of PCMs. We have also let's say various kinds of heat pumps, whether that's air to water or water to water driven heat pumps for hot water or space heating solutions. We apply also very innovative solution of long-term and medium-term storage that is aimed to be as loss-free as possible. And all of this, as mentioned before, is managed by energy management system as well. If we zoom into the demo cases, we have two on high level, two different kind of demo cases. One on the right side shown the demo case in France, and as typically for France, the buildings are prepared to be strongly electrified. And what we apply there is various kinds of technologies, as mentioned before, whether that is water-to-water heat pump, PCM electrical heaters, PV collectors, as well as PVT collectors. And the aim is also to apply a long-term storage system in this demonstration. Contrary to the, let's say, electrically driven system in France, in Austria, the system that we are using for demonstration is a district heating based system. So it's quite different configuration, and but the individual components are very similar to the system in France. If I go into a specific pictures of the demonstration itself, you can see that on the top, what you see a picture in France is a large residential buildings of about 115 small apartments used often by elderly people. Yet in Austria, we talk about 6 regular residential houses. So the configurations are quite different. The scale is also quite different, and the interface with the various kinds of grids is also quite different. Using this approach, we're trying to show and calculate also in our modeling tools what would be the impact of scaling up our solution towards the building stock at various places in Europe. I think that would be it from my perspective, and I would like to then give the word back to Susanna.
Thank you very much, Pavel, for the introduction of the SCORS project. Now going more into detailed information, the SCORS technologies, I would like to introduce Hans Hennig, energy engineer at Siemens, who will talk about the building energy management system developed for SCORS. Hans, the floor is yours.
Okay, thank you, Susanna. But before we dive into the world of building energy management systems, I should explain why you use one. Most cases or most buildings have a building management system, but it's simply not capable of handling energy as a control medium. They look ahead, but they don't really act on the information. Perhaps if you're lucky, then the solar radiation will be used. Otherwise, it doesn't work. As Pavel said, we have two sets of demo systems. You can see the generation equipment on top here and the equipment below the execution equipment. We devised a system in which the BEMS is kind of a brain above it. It takes in market signals, weather data, and domestic profiles, and it devises, a strategy, and it pipes that down to the execution equipment in the field. Same setup for Austria, slightly different. Oops, went too far. Slightly different setup, but same principle. Device from the top, pipe down to the execution. The system we've built consists of a server where the algorithms are running, where the logging is done, where the weather API comes in, some communication stuff, the controller that executes all the commands that have been set up by the BEMS, some interfacing equipment here, and some auxiliary equipment to make it all work, so power supply, stuff like that. On the server, two algorithms are running, one prediction algorithm and one decision algorithm. The prediction algorithm predicts, as the name suggests, all the stuff that needs predicting, like the solar energy gains, like the status of charges and buffers, the user profiles, stuff like that. And it devises a net consumption profile, basically how much energy you have left in 1 hour. And then the decision algorithm decides what to do with that amount of energy. And it can optimize either for self-consumption or it can optimize for cost. And what you're basically doing is calculating basically this curve, the curve that says we have energy left or we have energy shortage. And the job of the BEMS is actually very simple. You see this blue area where there's an energy surplus. We have to distribute that area over the area where there is a shortage. And in theory, that's relatively easy. In practice, as you can see here, the pictures from the simulation, it's a little bit more tricky, but it's doable. To do this, we've built some kind of an interface to see all the results of the field equipment. This one is for the domestic hot water system. You can see here the various signals. You can see the statuses. This one is for the CLC. And talking about the CLC, we do field tests to see if the equipment behaves as we want it to behave. So we've asked it to charge twice and to discharge a little bit further on. And what you see happening in practice is that the CLC indeed charges 2 times and that it discharges a little bit later on. When charging or discharging happens, energy is released, and you see the temperature in the buffer increasing. So that's exactly the behavior we want. One time we had an opportunity to field test without really testing it. We had a system error in the district heating. Building had to cool down over the weekend. You can see here the temperatures of the building in Austria. Supply 20 degrees. I got a call at 9 in the morning, so we switched on the system. And you can see the system delivered energy. Temperatures inside the buffer go down, inside the building go up. And around here you reach some kind of an equilibrium where the building is up to temperature again, and people are comfortable in there. At about 3 in the afternoon, the district heating was repaired again, and the systems switched off, and the temperatures inside the district heating system go up, and the buffer is replenished. Although we are in the middle of the testing period, and still an awful lot of work needs to be done, there are a few lessons we already can draw from this. One is, for all kinds of reasons, things go in another way than you planned. And to solve that, you need people with all kinds of different backgrounds, ranging from mechanical to electrical, but also network people or IT specialists. And they all have to work together, otherwise you cannot solve the problems that occur. When you look at the future, when you look at the future, you see a map of the Netherlands, and you see most of it is red. That means there's a problem with feed-in possibilities for solar and for wind. That means the systems like BEMS will become standard in the future, and very soon, because this is a problem you cannot solve easily. So in order to do that, you need some kind of self-learning BEMS algorithms to be able to cope with these large amounts of problems in the network. That's it from me. I'll hand you back to Susanna.
Thank you very much. We will need to skip this presentation, so we will go. Alexander did not join us, so we will skip straight to the next presentation, which is on heat pumps, and our presenter is Clement Dumont, mechanical engineer at Heliopac. So Clement, the floor is yours. Apologies for the quick change.
Yes, thank you, Susanna. Hello, everyone. I will do a quick presentation about the heat pumps from my company Heliopac that we installed on the demonstration site. So we have mature technology, and the main challenge into the SCORES project was to communicate with the BEMS, for example. Here is a schema about the installation on Agent. We have actually 3 heat pumps to provide the 3 heat pumps with a total power of 36 kilowatt to provide the domestic hot water for the building. And the system is the collector is on the roof, and we use PVT panels that are hybrid panels that provide photovoltaic energy and also works as a heat source. These panels are manufactured by Dualsun, that is a French company. And here we can see a photo of the I took on the roof at Agen. We can see the piping that is behind the photovoltaic cells that works as the heat source. On Gleisdorf, in Austria, we have a very different installation that is not a classic one, because the heat source is the district heating. So we built a dedicated system for the SCORS project. And of course, the heat pumps are linked to the BEMS from Siemens via Modbus communication. And the main learning in SCORS was mainly how do we communicate with the BEMS. We have to define the relevant variables and to adapt all of the regulation softwares. We choose to use variable flow circulators in Agen. This way we can improve the precision of the regulation, and they act in place of the usual on-off circulators. And the specific system in Gleisdorf is that we experience the dynamic stratification because the system works for both domestic hot water and space heating. And we have one water tank, and from this water tank, we have two outlets at a different height and so different temperature. And this is something we developed for the SCORS experimentation. Thank you. I will let Pavel speak again.
Thank you very much, Clement. As Clement said, our next speaker is again Pavel, who will talk about the seasonal thermal energy storage. So Pavel, the floor is yours.
Thank you very much. So in these several slides, I will show you the current status and example of how one can tackle a long-term storage of energy in or around buildings. To be very specific, I'm going to show you what is the status of the current CLC seasonal thermal storage technology, which we have decided to rename to a redox heat storage technology. Historically, chemical looping, or CLC, or chemical looping technology, has been developed for power generation applications where separation of CO2 is taking place. And it's also based on metal oxidation and reduction processes, as is our approach here. However, the technology has been adopted from industry towards built environment and scaled down significantly to be able to be applied in buildings. Major advantage of this technology over many other types of storage technologies is its inherent high energy density, which on system level should be able to use values of well above 1 gigajoules per cubic meter. In comparison, hot water reaches about 0.15 or 0.18 gigajoules per cubic meter. This technology of redox heat is relatively straightforward from the process perspective, and I will explain it to you on the picture on the right side. In principle, you can start within your storage system with a pure metal. In our case, we use copper. And when you heat it up and bring air inside the reactor, the oxygen in the air converts the metal to the metal oxide, so copper oxide. That process releases significant amount of energy, as effectively it's an oxidation process. If you want to reverse it, you bring into the reactor, the same reactor, hydrogen, and that process is in fact for copper also exothermic, so also energy is generated, and the metals converted from the oxide back to a pure metal. This process is quite reversible, and as I will show on the following slides. Before I get to that, I will first want to show you how the system is aimed to be connected to buildings. So what you see on this side, on the left side, is obviously an example of a building via heat exchanger, a buffer system. So buffer vessel is connected to the house, and inside the buffer are placed individual reactors from the copper, as I've described before, which can be using air from the pump or hydrogen from the hydrolyzer, converted to either pure metal or oxide, respectively. Water that's generated in the process of the oxidation is condensed and used later on for the process of reduction towards feeding towards the hydrolyzer. How does it really look like, however? So what you see on the left side here on the picture is a lab experimental setup where we have the developments and scaled the technology to appropriate size for the buildings. And on the right side, you see the example of the CLC or redox heat reactor, where inside of this red tube copper is placed. What you see on this picture is large amount of connections from the side, which are thermocouples or temperature sensing points, with which we are able to monitor and control the process of oxidation and reduction of copper. On the next picture, you see a zoom in into how the inner side, inside of our reactors look like. So you see also that this is the top view. So you see quite a number of heating elements over here to be able to start the reaction, and the reaction, after being started up and reactive gases are brought in, whether that is oxygen in air or hydrogen, continues from the top towards the bottom or bottom to the top by itself. So you only initiate the reaction at the beginning, and it goes through the complete reactor by itself, self-sustaining its own process. How does it look like from scientific perspective? What you see on this graph is temperature on the y-axis and time on the x-axis. And what you see is, as the time passes by, individual peaks are coming up and down. These peaks are effectively thermocouples, as I've shown in the previous picture, measuring temperature at various height, as you can see from the top to the bottom of the reactor. And what we see is that basically your heat wave passes nicely through the complete reactor from top to the bottom, reaching the end of the reactor and dying out at the end, because the process has been fully finalized. This technology has been developed over the last 4 years, and at the moment the status is that we have been able to reach about 0.5 meter of conversion system in 2 separate reactor points, meaning that the technology is currently effectively ready to be also demonstrated in the field. However, we had to proceed about 1.5 years ago with implementation of an emulator system into the demonstration, so the demonstrations themselves can also run. So unfortunately, the hydrolyzer as well as the copper technology has not been demonstrated in the demonstration sites. And in order to be able to enable the demonstration sites to continue through the testing, we have built an emulator systems that basically behaves quite dynamics in a similar way as the real system would. Again, you see a reactor here. You see a buffer system placed next to it via pumps. The energy is being pumped in there, and then via heat exchanger can be placed into the building itself. In practice, what you see on this picture is an example of the reactor, nicely insulated, and What you see further are examples of pictures of how the setup has been built. So what you see here is on the backside is the reactor, and behind that is the buffer vessel itself. What are the next steps? As I mentioned, the prototype of the redox heat reactor and the system has been built and fully tested in the lab. Demonstration system has been placed, an emulator has been tested and installed in Austria and works quite well. And the next steps would be then we have to look at two aspects mainly, and to increase the number of cycles that this reactor can manage to do from about 5, 6 to you need to aim to at least 20 or 50. And we have to also look critically on the cost of the system, as this is going to be a major challenge for the commercial application of this system. And I think this was the last slide, so I'll give back my word to Zuzana.
Thank you very much, Pavel. Thank you for the presentation. We will now come back to earlier topic, which is the phase change material, which will be presented by Alexander LeBlanc. Please go to 29. Thank you very much. He's a Research and Innovation Director at Kampa. Alexander, the floor is yours.
Yes, thank you. Good morning, everyone. On my side, we were involved to study the opportunity to use storage capacity located inside the room of the building. So especially with storage units using electricity as an energy source. Can you move the slide on, please? Yes, thank you. So yes, all the other storage technology use a space in the building not in the limit of the livable space. We studied, as you know, for storage, the volume that we can use is limited, and it brings extra cost. So we investigated the chance to use the indoor space to put the storage capacity. So, for example, on the picture on the right, you have the picture of the unit that provides heat for room heating, but also stores energy on demand. So it converts electricity as heat to bring thermal comfort in the room, and it's taking almost no space other than the floor space described on the picture here. So we had some constraints. Of course, as it's in the room of the inhabitant, it has to be as small as possible. But this is the same constraint as all storage units. Aesthetic, because it is part of the decoration. Quiet, also not to disturb the end user. Efficient, and also BEMS interfaceable. So please, next slide. Thank you. So on the technology itself, in the SCORES project, we investigated two versions. The one which is on the right here, which is Joule effect based, meaning we convert directly electricity to heat with no losses, but with a lower efficiency than the version on the left, which is heat pump based. So which use a thermodynamic cycle to convert electricity to heat, but with the constraint to use the cold source as from the outdoor air. So the heater on the left requires access to the outdoor air, which is an installation constraint. So the two prototypes were investigated during the project. Both have very various constraints, and we will see how it affects also the storage core, which has a different material. Thank you. Next slide, please. First constraint that I quoted before was to be as small as possible. So the first barrier we wanted to have been dropped during the project was to use, instead of classical heat storage heaters, which use bricks or cast iron risen up at a very high temperature, It's mostly above 400, 500 degrees, which brings the need to have a thick insulation layer to prevent the heat to go out of the storage core. We investigated the use of phase change materials, which is a very efficient material to store energy during the phase change. The phase change enthalpy of the materials we chose is very high, but it brings several constraints, including thermomechanical constraints. So when it gets from solid to liquid phase, it changes its volume, so it's hard to encapsulate. And the material also have a low conductivity. So both of these mechanisms make the material hard to put in service in a commercial appliance. So to solve the two problems, we worked with the partners of the project, and especially IPS, on simulation and mechanical tests to optimize the heat conductivity and to optimize the producibility to scale up from a lab prototype to an industrial production. So to encapsulate the phase change material in aluminum profiles, as you see on the right part of the slide, to manage to stack these aluminum profiles one above the other on the top right picture, and build a storage core made of phase change material. Thank you. Next slide, please. Next challenge was also to interface the appliance with the BEMS, as the energy that is stored in the appliance has an impact on the end user's comfort. The amount of energy that is stored in the appliance has to be precisely calculated, because nobody wants to be out of comfort in his room. To store energy and consume less energy, to use renewable energy is the main purpose of the project. But when you talk about comfort and indoor comfort of end users, you cannot accept a lack of comfort. So we worked on the way the load of the storage core is managed by the BEMS. So it's a mix between the presence absence schedule of the end user in the room, the weather forecasts, and the energy availability among all the others storage units of the building. Thank you. Next slide, please. So this technology, which is based on the FA Joule, is currently being demonstrated in Agen. So in the various pictures, I show you the building you already saw, but also the product on the bottom left picture, which is installed in the bedroom of this retirement home. So it's currently up and running and storing energy to bring comfort in this indoor space. Thank you for your attention.
Thank you very much, Alexander, for your presentation. Our next presenter is Michael Fischer, Business Unit Manager at Koenig Metal, who will present the heat battery. Michael, the floor is yours.
Thank you, Susanna. Good morning, everyone. Our main task in that project was to manufacture metal components for the CLC system, what Pavel already showed in his presentation, as well as implementing our GVI technology, which is very special and super insulation technology. And in my slides, I will go give you a briefly overview about that particular technology in the case of a heat battery. So what we did was to fabricate a heat battery, sensible heat storage by the use of water. We called it MK1, and we designed it especially for the purpose of the Austrian demo site. You already saw that container where the buffer tank were installed, and you can see on the screen the design what we purposed to. After design phase, it was necessary to design it. and went over into construction phase. As you can see here, the system consists of 2 walls. So our insulation technology is a double wall system. And in between we have a filling material which overtakes the filling purpose, as well as supporting the walls due to the vacuum which is applied onto. And on the right side laying, you can see there it's the inner vessel, which is already prefabricated. It consists of a dome head on the bottom as well as on the top side, and a tube. And standing here to the left side, it's the outer shell, which take place at the surrounding of the inner one. On the next page, you can see a welding process we installed. And as you could imagine, we have a vacuum insulation. It's quite important to have a system which is leak tight, that it durates the vacuum over a long time. So it's quite important to have a good ability to weld, as well as the quality aspects are quite important. That was the tank when it was ready for commissioning. So if you compare it to the design, it looks quite similar, and we sent it over to TNO in the labs to have a characterization. And after having the characterization, it went to the installation into the container, which was located in Austria, as you might have seen before in the slides from Pavel. And on the right side in the pictures, you can see our heat battery as well as the reactor, which were also produced from us. So the sister and the brother found together in the container in Austria. The performance values of that MK1 were quite impressive. So if you take a look at the graph on the left side, the blue line is the line which is the performance of our tank, and the x-axis on the graph, you should take a deeper look into it. It's not hours, it's days. And compared to existing systems, the values are quite good and interesting. So the next step was to think about in how the system could be sized to a bigger scale to bring it into a home. Therefore, we had a couple of discussions with TNO, and the final design looked like that. Project name MK2. The volume of that one compared to the first one. So the first one had around 100 liters. That one has 200 liters approx. And the value was given due to an analysis we made, analyzing the advantage of the PV systems installed in Europe, as well as the consumption given by a 2.5 heads household. So we arrived at 200 liters, and the vessel looked like that. So don't be afraid about that system in the background and on the bottom. So we need to install that the system is flexible and movable. Production phase, some pictures here, the laying vessel, that's the inner one again, so consisting a dome head and at the bottom as well as on the top side, a tube. It was quite long, so it was approx 1.8 meter length. Here you can see a picture of the system ready for shipment, and we already had a happy customer at TNO. So Lawrence really was excited to receive it and install it at TNO to make the characterization. And we found out that the performance values weren't as we expected it in the calculation. So we tried to have a linear scaling up on the system, but we implemented also some additional stuff which changes the performance a bit. So the next steps after the characterization of the MK2 was in how it fulfills our expectation to a very good system. And it ended up at a project name called MK3. The design is confidential, so I can't show it. The target and the goal is to industrialize that, but it's not a task for König Metall, KMG. It's a task for the company NES, which has been founded at the beginning of the year. And the founders of NES are 3 employees from TNO. One of them you saw, it's Pavel. And the goal of the company is to industrialize that product, the MK3. And we have a quite good situation as KMG because we act as a supplier as well as a shareholder in the company, and we have to trust and seeing there's a big opportunity for us to bring that product in a market. And the last information on that, and which is a quite interesting one, because that cooperation in the NEST project, as well as that MK3, is a direct outcome of the SCORES project. So we not just only took place as a partner in the SCORES project, which is an R&D project. So we have a directly connection to the future, and this is a really good situation. And thanks to SCORES, we found a collaboration, a way to establish now NES and bring that product to the market. Thank you for your attention.
Thank you very much, Michael. Thank you for the presentation of the good outcome of the SCORES project. Now to show the demonstration of the technologies in more detail, we have our next presenter, Gilles Plessis, research engineer from EDF, who will present the demo site in France. Gilles, the floor is yours.
Thank you, Susanna. Hi, everyone. So we've been seeing in the previous talk, we've been seeing in the previous talks the different technology we were testing in the SCORES project. So those technology don't have the same technology readiness level. And one of the main, let's say, objective also of the SCORES project was not only to develop those technology, but also to test them in real life. So test them with the simulation, but also test them implemented in demonstrators. And for that, we've been choosing two locations, as Pavel mentioned at the beginning of this final event. We've been choosing two locations, one in France and one in Austria. So basically, the demonstrator in France is located in the south of France. So it benefits from a warm oceanic climate, meaning that we don't have so much energy need, I would say, for space heating. So roughly, I put the figure here, roughly 2,000 heating degrees for the city of Agen. And one of the main also criteria for choosing this demonstration site was that this is not connected, or the building is not actually connected to a district heating. The overall context in France, it's that we have a large share, I would say, of electric-driven heating for both domestic hot water and space heating. And this makes the system, the overall system, very with a high thermal sensitivity, I would say, so roughly 2.5 gigawatts per outdoor degree. So the main challenges, knowing that, are of course energy efficiency, but it was a bit aside from the SCORES project, I would say. Introducing renewable energy, and part of that being renewable electricity, of course. So we'll see that in the later slide, and also increase flexibility to deal first with intermittency of renewable energy, but also to be able to build buildings that are grid friendly, I would say. In this work package 8, we've been demonstrating several technology, optimizing also the operation between those technology, and see how this can perform or cover these challenges. Second objective also to increase self-consumption, of course, and self-production in systems that are economically viable. That's also a main criteria for us. So demonstration site was chosen as a residential collective building. So a bit more than 100 small flats. And the building is quite large, as Pavel mentioned, so more than 6,000 square meters. And it's including also services, so it's a residential residents that include several services like collective catering, swimming pool, and else. But in the SCORES project, we'll only focus on domestic hot water, space heating, and HVAC usage, I would say. Recent building also, so this is compliant with the 2012 building regulation in France. So meaning that the insulation, for instance, are quite good for this building. In terms of technology, in this demonstrator, we were, so the building is mostly for the space heating supply by regular air-to-air heat pump, I would say, a VRV air-to-air heat pump. So this is not part of the SCORES project, but in the SCORES project, we were implementing and installing several systems on this building, which are actually some systems focused for covering the domestic hot water needs, so PVT collectors, photovoltaic and thermal collectors, coupled to a water-to-water heat pump, 3 actually of them, 3 times 12 kilowatts, and hot water storage as sensible thermal storage, I would say. We've been also installing second life electrical battery from 4C Powers, so to deal with surplus of electricity, as mentioned also by Hans from Siemens, and also electric driven heaters, including latent heat storage in form of PCM, thanks to PCM, sorry, in two apartments only. On the overall system is also coordinated by the BEMS from Siemens, so Building Energy Management System. So you can see on the bottom of this slide several pictures of those systems. So first, PVT plus water-to-water heat pump and water tank, hot water tank. Electric heaters from Kampa, 4C Powers batteries in this picture, and then the BEMS also schematics. So the demonstration phase started a few months ago. So we are still working on this and still analyzing the data to be able to give qualitative and quantitative analysis on the performances of all these components individually, but also on the overall system. So basically, one of the outputs for now are the split between different usage. So we can see, for instance, the heating and comparing the space heating needs provided by the VRV system between 2020 and 2021 last year. Cooling also demand, domestic hot water also. And the figure, I would say, on the right side is also showing performances and energy, part of energy coming from the domestic hot waters from Heliopac. So you can see the bar graph in red that are representing useful energy for thermal energy for providing domestic hot water. And then you have electricity that is needed to actually provide this thermal energy. So you have usually a large share of electricity that is used for the heat pump and a small part which is used for the backup. So basically the COP, coefficient of performance, is quite good, around 3, I would say, and even so it's real life demonstration also. So we observed some issues in interfacing between the different components of the system. So that's why at some point we had some huge part of backup consumption, but those problems are mostly solved now. I think that's all for my part. I don't have so much detail so far. As I said, the phase is still in progress, and I will leave the floor again to Susanna.
Thank you very much, Jill. Our next demonstration site in Austria will be presented by Wim van Helden, head of the Department of Technology Development at AE Intec. Wim, the floor is yours.
Thank you very much. Yes, the demo site in Austria, it's like in Agen, it's meant to get more experience in practice with the systems that were devised in the SCORES project. The system in Austria, next slide please, is a mixed use system in the sense that it consists of 2 office buildings and 2 residential buildings that are coupled to each other. It is a complex that has been built in 1989, already with very high efficiency standards. So the basic energy consumption of the building is low. So on the left you see the office buildings, on the right the residential buildings. It's also connected to the district heating network of Gleisdorf. Gleisdorf is a small village situated in the southeast of Austria, near to Graz. And in the almost left corner, you can see a small lawn on which the test containers have been placed, where the equipment of Siemens and Hydropack, and 4C Power and of TNO was situated. Next slide, please. So this is how it looks like, the energy system. The houses itself and the offices have a heating system that is wall and floor heating, so it's a low temperature heating system. It's also, it has a balanced ventilation system with heat recovery. And there's also additionally the possibility of having a cooling through the heating system, so through the wall and floor heating in summer by an absorption heat pump, and also a compression heat system, a cooling system. To the right, you see some pictures of the equipment that has been installed. The 2 left pictures are inside the office building where the boiler room is. The 2 yellow and blue devices are the heat pumps from Hydropack. They consume the electricity locally as much as possible, and the heat then generated, if not used directly, is stored in the green vessel, which is on the bottom left picture. Then, as mentioned at the outset, there were 2 containers. One container pictured here is the container with a PV system on top of it, and inside the container is the BEMS equipment. And the heat batteries, as depicted here in this case, we have 5 electrical batteries from 4C Power. And also in this container is the converter system for the PV and battery control. The other container consists of the CLC and the heat battery from König Metall and TNO. So what are the key technologies? We have PV panels. They are combined with water-to-water heat pumps, as depicted here, and the 2,000-liter storage. We have the second life electrical batteries, and we have the electrical-driven chemical looping combustion storage unit, which, as Pavel explained, is emulated in this system. And of course, the building energy management system. And the fact that Gleisdorf has a combined functionality, so not only offices but also residential function, makes say the functionality, or makes the target for the BEM system more complicated than when it would only have been one functionality. This is what we would like to show about the Austrian demo, and I'll give back to Susanna for the remainder of this presentation.
Thank you, Wim. The next portion of our event is the Q&A session. We have received some questions, so partners or speakers have prepared answers to those questions, so we can go to the next slide. The question we have is, what happens with the heat production during the night? And we have answer prepared by Clement. So Clement, your answer.
Yes. we can wonder what happens heat production during the night regarding the heat pump and domestic hot water production. Actually, the solar heat collector that we use, can you shift to the next slide, please, Susanna? The roof collectors that we use are collecting the heat from the ambient air and the atmosphere more than only the radiation. So it's yes, 80-20 ratio. So it can also work quite well during the night if the ambient temperature is not too low, of course. Yes, it's a convective transfer actually. That's all for me.
Thank you very much. We have another question about the building energy management system. And the question is if it can be technically implemented in any building. And answer will be by Hans.
Yep, can you go to the next slide, please? Okay, the answer is basically yes and no. No, because a couple of things need to be in place before you can use such a system. You need to have some kind of energy storage, or you need to have equipment that can be controlled. For example, if you have an office building and you want to switch off the lights, yeah, that doesn't work in practice. So energy savings there is a no-go. So you need either a battery or a storage tank or stuff like that. What would be nice to have in this case would be smart energy meters. So you can draw up a profile based on outside temperature, based on weather conditions, based on the time of the day, because Monday mornings look slightly different than Friday afternoons. So the better your profile and the better you can predict the profile, the better you can predict what will happen, and the better a decision can be reached from the BEMS. And of course, what helps to make the BEMS economically feasible is when you have some kind of pricing scheme that's favorable. If you have very good conditions for delivering back to the grid in Holland, they're not that great, frankly. You get 3 cents per kilowatt hour. That's almost nothing. And if you compare that to the cost of electricity, there's a mismatch. If those prices are better together, then the implementation chances are much better. I'll hand back to you.
Thank you for the answer. We have another question for you. What does the control loop of the system look like, and what systems can be connected? Okay,
that's a slightly more technical question. Can you go to the next one, please? I had some backup slides. What you have in practice is that you have a field equipment that communicates somehow with the BEMS. So you use either Modbus or BACnet or some kind of protocol that the controllers can interface with. So you need communication. From there, all the stuff enters into the controller that changes let's say the local communication language to something that it can understand. And in our case, that's BACnet. It builds BACnet objects because they're fairly easy to work with. Those will be transferred to the BEMS system, and they can make sense of what's happening there. Based on that, it will devise a strategy, and the strategy will be communicated back to the controller and back to the interface units, back to the field equipment. And once again, once the field equipment acts, the controllers will sense, okay, something is happening, and it will feed back that information to the BEMS as a check. The second part of the question is which languages can be connected. That can be, as I said, BACnet, but also KNX, or there are a couple of more. Depends a bit on the strategy, but in principle, from the protocols that are available, about 50% can be used.
Follow-up question we have. So what happens when we want to connect a non-standard to the BEMS?
Okay, well, the BEMS is made out of modules. And every module, for example, a heat pump or a CLC, has a separate module. And once extra or other equipment is connected, then we have to insert a new model into the BEM system. And that model can contain either anything standard, or we can program it ourselves to see what's to mimic the behavior of the equipment in question. So you can change, let's say, a system that is already running, or update it, or do something with it to map basically reality. And the fact that it's modular simply means you put it in, and the BEMS will see, okay, I have a new module, this equipment, and it will take that with it in its decision.
Thank you very much. We have run out of time for more questions. We have received some more, so we will keep those for the panel discussion if there's time. Thank you very much, Hans, for answering. Now we would like to give floor to our cluster project, HiBuild. We have a presenter, Mireia Fernandez-Noirat from COMSA company. She's head of the Technological Innovation Energy Unit in the Research and Development Department. So Mireia, the floor is yours.
Hello, good morning. Good morning, everybody. My name is Mireia Fernandez, and I am from COMSA, and I'm the project coordinator of HiBuild. Okay, first of all, I would like to thank you to the project Scores, our sister project, for giving the opportunity to us to present this project into this forum. Okay, sorry, went too far. Yes. The project was going to be presented by myself and by UDL, University of Lleida, but they cannot attend the event. So instead, ITAE CNR will be presenting the technical part. So I will be presenting the HiBuild in a nutshell, and after me, it will come Valeria Palomba to present the rest of the project. HiBuild is an innovation project funded by Horizon 2020 about the innovative compact hybrid electrical and thermal storage systems for low energy buildings. Okay, the project started in October 2017, and it will end in March 2020, so next month, after 54 months. And is a real research and innovation action, and the funding is almost 6 million euros. The consortium is formed by 20 partners among 9 countries in the UN. Okay, here you can see all the partners. It's COMSA, as I said before, we are the technical coordinator, the coordinators, the general coordinators, and then University of Lleida, they are the technical coordinators. The rest of the partners are ITAE CNR, AIT, University of Cyprus, NTUA, R2M, EURAC, Fahrenheit, CSM, Stress, Micrometal, Pink, Engineering, Ochner, Daiking, AKG, Municipality of Almatret, Novatec, and Municipality of Aglancia. In the HiBuild project, 2 innovative hybrid storage concepts have been developed. One is for the Mediterranean climate, and primarily for cooling the energy supply. Associated with this concept, there are two demos, one in Aglancia in Cyprus, and the other one in Almatret, close to Lleida in Spain. And then the other concept is for the continental climate, and it's primarily meant for heating and domestic hot water supply, and is located in Austria, in Langewan, Austria. The project is based on these 4 innovative components that you can see here in this picture: the DC powered reversible heat pump, the DC bus generator, compact sorption module, and the high density latent storage. And now I give the floor to Valeria Palomba from ITAE CNR, who will be presenting the rest of the presentation. Thank you very much.
Good morning, everyone. Next slide, please. Okay, so the Mediterranean system, as Mireia already said, is mainly meant for cooling dominated climates. It focuses on vapor compression heat pump that is connected on the evaporator side to, or includes on the evaporator side a low temperature latent storage consisting of three fluid heat exchanger where the refrigerant, the heat pump, the PCM, and the transfer fluid for the distribution system coexist. And on the condenser side, it is connected to sorption storage that allows a better operation of the heat pump by lowering the condensation temperature. In addition, electrical energy is stored by means of high density and long life lithium titanate oxide batteries. Next slide. Yes, please, next slide. Yes, as I was saying, the sorption module is a part of this. Next slide. And this is the latent storage. Next slide. And we have the electrical storage. For the continental system, the main component is the vapor compression heat pump connected to a three fluid exchanger on the condenser side for domestic hot water provision. Next slide. That you can see here. Next slide. The high temperature latent storage is connected to building apartments through the pink inner box solution. Next slide. And we have the electric storage connected to DC bus as well. Next slide. We have three demo sites, as Mireille already said, one in Almatret, one in Wangenwange, and one in Glansham. That apart from the technical solution include the advanced control developed by engineering and UDL using artificial intelligence techniques. Next slide. This is the overview of the project. So we started with the definition of the KPIs of the system and the first design of the system. Then during the second year, the components were tested in lab scale, and at the same time, the advanced control were developed. Then from the third year onward, we started the installation in the sites and the subsequent monitoring, which is still in place right now. Next slide. These are some pictures of the systems installed in the lab. So the picture on the upper part is the continental heat pump in the AET lab system laboratory, while the pictures on the bottom refer to the Mediterranean system installed in our lab. You can see on the left the heat pump with the integrated latent storage, then in the middle the sorption module, and on the right the DC bus with the electrical storage. Next slide. And these are some pictures of the system installed in the Mediterranean demos. On the left, you can see the linear Fresnel collectors, whose main feature compared to the other standard commercial system is the fact that they are done with smaller size mirrors, which allows a better focusing and also a better scalability of the system, also for non-industrial or large-scale application. And then the DC bus connected to the sorption module and the storage for the sensible storage for the linear Fresnel collectors, and finally on the right the heat pump. while the pictures on the bottom refer to the demo site in Aglancia. Next slide. These are some pictures of the system installed in Langenwang that was mainly intended for testing under winter conditions. So the installation took place during 2020, and then we have already completed at least 1 year of monitoring of the system. Spring data are also included. It's possible to see that several KPIs were addressed and system management occurred through the advanced controls developed. Next slide. Apart from the technical assessment of the performance of the system, attention was put also on the environmental, economical, and social aspects of the deployment of these technologies. So an LCA was carried out by UDL that allowed to identify the main points where environmental performance or environmental impact of the system occurs. And lifecycle costing was also recently completed. And thanks also to stress and RINA, social lifecycle assessment was carried out according to UNEP guidelines, and it was possible to see that the social impact for the system is quite good, indicating that even though some improvements are needed, as it is to be expected by technology that is under development now, it can be or it is socially accepted. Next slide. So to summarize what we achieved within HiBuild, according to what was the main goal before starting a project. So we had high efficiency conversion and storage, so using electricity through heat pumps to convert it, that was fully integrated with storage systems. All the systems can work under different modes. So for the Mediterranean climate, the main focus was to achieve high efficiency in cooling provision, and for the continental climate to achieve high efficiency in domestic hot water and heating production. And thanks to the inclusion of the desorption storage, it's also possible to work at different time scale and to address services to the grid, both for daily fluctuations and peak shaving with the latent storage and electrical storage, and long-term using the thermochemical system. Next slide. Finally, some key impacts from the project. You can see here that 19 papers were submitted and 18 published. All of them can be found on OpenAIRE and on Zenodo. I encourage you all to have a look at them. Next slide. And at the same time, the project was participating to different dissemination events, also in synergy with other European projects, such as the Sustainable Places conferences, and as part of the renewable heating and cooling platform. Next slide. And 2 patents were filed regarding the integration of the PCM inside the heat pump, and some of the key exploitable results are also available on the Horizon Result platform. Again, I encourage you to have a look at them. Next slide. Finally, we identified which would be the future of HiBuild technologies, and most of the partners are willing to continue with the development of the technologies, especially regarding the storage components and the advanced control. And the idea is to exploit Horizon Europe fundings and national fundings for bringing these technologies to TRL9 in 2 to 3 years for most of the components. Next slide. So just to conclude, within I build 2 systems that include the thermal and electric storage, and power to it systems were deployed and brought to TRL6 by demo site installation and monitoring. The environmental, economic, and social aspects were considered, and business models were also developed, which foresee the commercialization of most of the components for in the market in a couple of years, while for the overall system deployment in residential or commercial buildings, further development is needed. Thank you. I think this is the last slide. Of course, we will be available in the panel afterwards for discussion.
Thank you very much, Valeria. As Valeria said, we will hear more from Hybrid during the panel discussion, where we can compare the results of these 2 projects and discuss further. And now let's have a break. It's a bit more than 5 minutes. We will begin again at 11:25. So see you then, when we will discuss the future of the SCORS technologies. So see you at 11:25. And welcome back from the break. Now let's look at the future with the SCORS technologies, looking first at the system simulation with Keith O'Donovan from research at AE Intech. So Keith, the floor is yours.
Thank you, Susanna. Check my control. Okay, so yeah, thank you everyone who's still listening. So I'm going to firstly address the topic of system simulations, which were a pretty significant part of the project. And firstly, to address why we need system simulations. So in the project, they serve two purposes. And the first one was to be able to test the BEMS algorithm in a virtual environment before actually commissioning it on the demonstration sites itself. And the second function of the system simulations were to evaluate a number of scenarios for so-called SCORS future systems, where we have the ability to scale up our storage and PV technologies such that self-consumption can be optimized. So not just storage capacities, but also external electricity markets, so we can assess the impact of either flat tariff or day-ahead pricing schemes on the economic performance. So like the demonstration systems, we modeled both the French and Austrian buildings in the simulation environment, alongside all of the individual subsystems that make up these buildings. And for each
We have lost you, Keith. Can you hear us? Okay, let's give Keith a chance to come back. Let's continue with the presentation. Let's go to the next presenter, which is Claudia Portolano from RINA Consulting, who will present the market assessment of the SCORS system.
Thank you, Susanna. Good morning, everyone. I hope this short presentation may give you an overview of the qualitative market assessment analysis which has been provided during the project. I tried to have my control. Sorry. Okay. Okay, in this slide, an assessment of the market of a hybrid storage system is provided, analyzing three of the key markets linked to the SCORS 1 and the drivers and barriers the market is characterized by. The market of the global hybrid battery energy storage system was valued at $35 billion in 2020 and is expected to grow at a compound annual growth rate of 7.5% to reach $58 billion by 2027. Europe in 2020 represented the second geographical area in terms of market share in the sector, following North America. Also, the energy storage market shows a steady growth in terms of market revenues experienced from 2016 and 2020, and it is expected to continue increase by 2025. Also, in this case, Europe owns the second position by market revenues level after East Asia and Pacific. For what concerns thermal market, in the figure it is possible to observe the most developing markets in terms of growth rate. The best performing markets are located in Asia Pacific, America, Middle East, and Africa. Europe doesn't show a significant growth rate, but from the market size point of view, it represents the third area. The most important market drivers are those reported in the slide, so the backup power, electric thermal, the solar photovoltaic and other distributed generation systems, and the recent sharp increase in prices. As barriers, we can analyze them by two sides, barriers to the growth of stationary energy storage market and the barriers to the development of current PCM heat storage products. For the first kinds of barriers, we can find as examples lack of familiarity with storage technology, high upfront cost, the need for highly skilled and experienced technicians, and regulations preventing third-party or customer ownership of certain gears and preventing storage from ancillary services and capacity. Barriers to deployment of carriers PCM heat storage products instead. Some example could be limited customer knowledge, a lack of supply chain for PCM products, the availability of safe, reliable PCM materials with melting points suitable for most heating technologies. In this growth market context, we could imagine to launch the SCORE system on the market with an only example of a business model. This is just an example. This example foresee where the project involved companies are joined in a partnership with the aim to pursue the diffusion of the SCORE hybrid system, commercializing it directly to the building owners, so the end users, and to the ESCOs, which can then install the system and sell the energy service to the final end users. The value proposition will rely on the innovative content of SCOREs, which allows the increase of self-consumption and the reduction of the energy bills, maximizing the self-production. We can imagine the sale of different packaging services, customizing the system with different technologies in order to satisfy exactly the customer's needs. And this will reflect also in potential different prices at which sell them on the market. The SCORE hybrid system will guarantee mid and long-term storage of a surplus of cheap heat and electricity, avoiding expensive peak loads, improving the resilience of the grids. And for what concerns its structure about the cost, they may rely on the cost of a single component and all the operational and marketing cost to improve the commercialization of the services. To be able to reach this kind of model, the SCORE hybrid system needs to further technology developments to be ready for the market entrance. The components need to be scaled up in their production to reach the mass production scale volume and further reduce their production cost and be allowed to be sold at competitive prices, entering in the growth stage of the SCORE product life cycle. But once the technologies will be reliable and its price is more competitive, thanks to its great potentiality and the high competence of the partners involved in the project, it will be hopefully foreseen, and we believe in it, a potential widespread diffusion of the system, allowing to enter in its maturity stage and to offer at full level all its innovative content to the end users. Thank you very much. It's all for my side.
Thank you very much, Claudia, for taking over the presentation after Keith. We have Keith back, so let's go back to his presentation, which stopped at slide 121. So let's see if he's back. Welcome.
Hello again. Sorry about that technical problem. So we got as far as 121, you said?
Yes.
Okay.
If it helps, feel free to switch off your camera.
I might do it just to be safe, but so I'm just trying to take control again. Okay, so just back to what we were discussing, that for each simulation case, we defined respective reference case buildings and self-generation cases to see the impact of introducing the PV system and heat pumps alone. And then finally, the SCORE's future system builds further upon our self-generation case with the inclusion of the storage technologies such as the electric batteries, the CLC and PCM, as well as the BEMS algorithm, which regulates the charging and discharging of each of these storages such that self-consumption can be optimized. And the general workflow for the simulation was to build up a physical model of each building in Daimler simulation environment. And the main parameter inputs which we investigated are namely the storage capacities, as well as different electricity pricing tariffs. And as the simulation runs, it's constantly exchanging data with the BEMS algorithm, so sending information to and from the BEMS. And at each time step, the BEMS is looking ahead a couple of hours to predict upcoming surpluses or deficit in PV energy. And based on this, the BEMS sends controls back to the simulation to decide whether to charge or discharge any of the storages, including the battery system or more long-term storages such as the CLC reactors. And so the main outputs from the simulation, then we can see a number of technical performance indicators, such as the degree of self-consumption and the relative reduction in electricity or heat from the external grids. And as a separate step then in another work package, there's a techno-economic analysis which is carried out on each of these future system cases, where overall savings and levelized costs for each of the individual technologies can be analyzed. And this should assist in choosing an optimum scores configuration, both in terms of cost and self-consumption. So here's just an example of some outputs based on parameter sweeps, which we've carried out. This is for the French future system. So for a range of different battery capacities, we can see the increase in relative reduction of grid electricity with respect to our reference cases. Also of interest to us was to compare the difference in behavior when we look at either flat electricity price tariffs, where we only charge our battery system with excess PV, or on the right side, we see a case where we ran with day-ahead electricity prices, where the batteries are also being charged at short notice from the grid during periods of cheap electricity and discharging during the expensive periods. So all of these inputs are investigated in the system models and are to serve as a way to see the performance of our system if the individual technologies have reached the stage of maturity which could not be demonstrated on the actual sites. So the general outlook is that we could see very high reductions in grid electricity with these assumptions in mind. Regarding cost, there's still a lot of uncertainty about some of these technologies as they are in their early stages of development. There is ongoing work still now with the simulations as the demonstration sites are running. Another task, as mentioned at the beginning, is to use the simulation models to make a comparison with the real behavior of the BEMS in the demo and to validate as far as possible the monitoring data. So that's essentially it for me on the simulations. Thank you for being patient to listen to some slides twice. So I move back to Susanna now.
Thank you very much. Thank you, Keith. Our next topic is the social impact assessment of the SCORS project, and the presenter is Adelia Gafurova from Phoenix TNT. Adelia, the floor is yours.
Hello, everyone. Thank you. In the work package 9, we have task 9.5, according to which we need to ensure acceptance by market participants and end users, individual behaviors and choices to be analyzed in a socioeconomic context within the European region. In month 54, which is April 2022, we will submit deliverable 9.9, potential social impact of the project and users' engagement. For the last year, we have been conducting the survey with the purpose to collect the views of different stakeholders and identify their preferences related to hybrid energy storage systems. The questionnaire is short, simple, and consists of 8 questions, 7 of which are multiple choice questions. It was promoted through the project channels, such as project social media, project website, and network of connection of partners. As you can see from question 1 and question 2, most of the respondents are end users and researchers, predominantly from France and the Netherlands. Question 3 asked which buildings are most suitable for the integration of hybrid energy storage systems, and you can see that responses are distributed similarly between all options. Question 4 tried to find out how respondents assess their knowledge of hybrid energy storage systems. You can see from the graph that most people answered between 5 and 7, which means they are relatively aware of the technology. Question 5 figured out that the most important factors for the respondents if deciding to adopt the technology are profitability, low environmental impact, and energy efficiency. Answers to the question 6 showed that high investments and immature technology are the main barriers that are likely to prevent from adopting the technology. 69% of respondents would want to be involved in manufacturing, installing, or using hybrid energy storage systems, which is definitely a good sign. And finally, question 8 was an open question asking to share their opinion on the technology. As you can see, most answers are very positive about hybrid energy storage systems. You can see such comments as promising, crucial, essential, that it is a promising, crucial, and essential technology for the future. However, there were some also negative statements, for example, that it is a good idea only on paper, that it is not worth the effort, and that there is no skilled labor for that. Well, the point is to analyze all feedback and to adjust the technology development accordingly. Thank you.
Thank you very much, Adelia. We will, of course, share the results of the whole assessment on the project channels and on the website. Our last presenter before our panel discussion is Luis Coelho, professor at Instituto Politécnico de Setúbal, who will present the training activities of the SCORES project. Luis, the floor is yours. Please unmute yourself and you can start.
Okay, yes, sorry. Good morning, everyone. So I will make a brief presentation about the training activities. Can you pass next slide, please? Okay, so the objectives of the training activities are to perform training activities exploiting instructions, processes, and tools developed in framework of the project, and distribute them to a wider community of professionals relevant for production, design, application, and installations. So supporting activities to include videos, seminars, webinars, and courses, and 2 training demo site seminars will be organized. So next slide, please. Oh, sorry. Okay. We have produced 8 videos related with different technologies developed in the project. So you can use this link above to access the videos, and the videos will be available on the SCORES YouTube channel next week. Oops, very sorry. Okay. We organized one webinar about innovative renewable solutions for residential buildings. It was organized within the event World Sustainable Energy Days last June. And now we are preparing the second webinar about towards total decarbonization of buildings by 2050, the role of the SCORES solution project. So we will provide more information soon, and I hope that you have your interest and your participation at this webinar. And now we are also organizing the training course on thermal energy storage for heating, cooling, and domestic hot water for buildings. This course will be held physically at the National Energy Agency facilities in Lisbon, Portugal, on 1st of April. We will also provide more information soon. And the last training activities is about the 2 training demo site seminaries. We also are preparing these 2 training site seminaries online. So we will organize one training demo site seminary about the demo site A in Glasgow, Austria, and the second one about the demo site B in Agen, France. So we will also provide more information soon, and I hope that you are able to participate in these the different training activities. Thank you very much. And now I pass the floor to Susanna. Thanks.
Thank you very much, Luis. We are very happy to invite you to all the other events the project will be organizing. Now, let's move to the panel discussion. Moderator of the discussion will be Pavel Bodic, but we of course invite all the partners, all the speakers to join in and discuss, mainly in cooperation with HiBuild, to kick off the discussion and to introduce. We have a question from the audience to Pavel, who was mentioned is one of the partners who is in charge of the main result of the project, or one of the results of the project, the new company which will be established. The question is there a timeline for this new company and when the products will be available?
Well, thank you for the question, and thanks for the introduction, Susanna. The new company has been established in January. The timeline for bringing the products on the market is we start with the field tests from the middle of this year, and a small scale, think of thousands of pieces production will be made. Will start in 2023. So in principle, orders can flow in at any point in time with deliveries in about 1 year. That would be the answer to the question. And then from the perspective of the panel discussion, Zuna, do we have more questions available from the audience? Because I don't see any in the tool here.
Not currently. So.
Not currently. So in the meantime, I have a question to the HiBuild team, and I'm not sure who to address it. I'm going to address it to the HiBuild team as such. First of all, really nice work and very nice progress in many technologies that you guys have, let's say, taken the next step in the HiBuild project. I was wondering, what is the status, or could you tell a little bit more about the control systems in the buildings themselves? Are they demonstrated as a scientific type of control systems, and how do you plan to commercialize that aspect of your demonstrations? Do we have the HiBuild team online?
We should have Valeria or
Yes.
Yeah. Could you hear well my question?
No, can you repeat, please?
Yeah, no problem. So the question is that you have shown very nice technologies as they were developed in the project. One thing that I would like you to elaborate a little bit more is the overall control system in a building. So let's say a building management system as such. How was this developed, and how do you plan to commercialize it or to bring it to the next TRL step?
Okay, so the control system was developed by engineering and UDL, and it's meant to. There are two levels of control. So there is the low-level control and the high-level control. The low-level control relies on the platforms and systems already in place by the manufacturers or the various technologies. So basically commercial PLC, while the high-level control is running on an industrial PC right now. And basically it takes data from takes weather data, electricity data from the grid, and sends the input to the low-level controllers. From the exploitation point of view in the future, the idea is to refine the control also within other projects that have already been funded. And finally, there has not been a discussion on possible patents or software for commercialization available. So this is still an open discussion. I don't know if this answers to your question.
Yeah, I think that's clear. So it was university developed at UDL, and you're looking at taking the next step in the follow-up projects to bring it closer to the market.
It was developed by UDL and engineering, which is
oh, there was an engineering. Okay.
Commercial multinational company with headquarters in Italy. So the idea is in case to develop that based on engineering platforms.
Yeah, clear. Oh yeah, I see. I was also I thought it was UDL engineering as part of your part of the university, but I see now in the names of the companies in your one of your presentation sheets that that's indeed a partner. Clear. Well, thank you very much. I'd like to invite all other participants from both this course and hybrid projects also to let's say ask questions of an interest that they have.
We have another question since we heard about the follow-up activities of HiBuild. Are there any follow-up activities also for scores except the ones we have talked about?
Maybe this question to all partners. Please speak out. So in the meantime, I can say that for TNO, we have a continuation together with some of the scores partners and aiming to submit a proposal in the coming call on the thermal energy storage of Horizon Europe. I believe the deadline is late April. And we plan to take the concept of thermal energy storage systems in buildings to the next level in that call.
I would say from a Siemens perspective, Hans Hennig here, we learned a couple of things during the project, and that's already finding its way into our, let's say, products in the Netherlands. So things we saw in the field, like, okay, you need to include these and these variables to do some stuff in the future. We already put that in our products right now. So that's ongoing. For the future, I'm not sure. That's something up to headquarters, but I assume we'll continue with this.
Thank Hans. Other technology partners looking at perhaps Heliopac with their effectively a commercial system. What are your plans forward? Not sure if we have everyone online still.
Yes, I'm
hey,
here.
Clement, thanks.
Yes, so on Heliopac point of view, it was nice to develop a Modbus interface, and also we took advantage of the SCORS project by implementing, for example, new circulators into our system, like intelligent ones, and we learned from that, and this way we can move on with that. With it.
Yeah. All right. I have myself still maybe a question to which I'm always curious to ask to all partners that develop storage technologies, if they could comment on the energy density of their systems. There's always this beliefs that specific technologies are limited in their specifications to how much energy can be stored in certain volumes. For houses, that is very critical aspect. So maybe from if the storage technology providers in scores and perhaps also Valeria for HiBuild could comment on the energy density on a system level that their products or future products could count on. And maybe I'm just looking at the list. Alexandre mentioned that he had in the chat that he had problems with audio, so I'm not sure if that has been fixed. If not, then maybe Valeria, do you have any comment? Because I know you used a latent storage system.
Yes, but the latent storage system that we used was optimized in order to be embedded within the heat pump. So the majority of effort was put into producing a design that could be suitable for the integration of the heat pump. And as I said, this has also been patented by IIT, EKG and Oxner. Regarding the option storage, still some work is being done, because the configuration of the system is still being optimized. We have also under other Horizon 2020 funded calls some projects ongoing in which we are planning to realize the actual cascade integration of the absorption storage with the heat pump with a lower number of components. So as it is so far, we have actually a full absorption system with the absorbers and condenser and evaporator, and it is connected hydraulically to the heat pump. Within other projects, we are aiming at creating one single component that shares an integrated evaporator condenser for the heat pump, so to further reduce the density of the system. Let's say that compared to commercial systems that can provide more or less the required capacity by multifamily buildings, we highlighted more or less 20% higher energy density for the overall system.
Clear. Thank you very much. Very nice. I don't have myself more questions. I'm not sure how much time we have left, Zuzana, but I think a couple of minutes left to go. So there are still opportunities to join the discussion with either observations or questions to other participants.
We can see Wim. Do you have anything to share?
Yes, I would like to share the fact that in parallel also we are working on compact thermal energy storage module and system development. And in a recently finished project, we arrived at say 140 kilowatt hours per cubic meter for hot tap water and room heating applications. But as you mentioned, Pavel, it's really very important to make sure that you have the proper definition of what the storage density should be. So taking into account also the volumes of those components that you need to charge and discharge your module. So on a system level, this would lead to not 140 kilowatt hours per cubic meter, but to say about 60 or 70 kilowatt hours per cubic meter, because you also need to account for the volume of the additional components. And in a Austrian-funded follow-up project, we will demonstrate these absorption systems both in a hotel restaurant setting and also in a single-family house. So we would like to make there the next step into showing that this storage technology is demonstrable.
Nice. Thanks, Wim. I see Gilles also joining.
Yeah, I mean, I was thinking about your question, Pavel, on project perspective and what this project brings us and what could be the next step, at least for EDSO. We are not a technology provider as such. We are more focusing on our role of electricity producer, or I would say grid operator, even though we have some business unit in self-consumption for residential or B2C clients. But nevertheless, one of our main goals is to be able to anticipate what could be the impact of such system like the SCORE systems on our production assets and also on the grid. So making also this building grid friendly, as I said, be still a big challenge for us. And we want to make sure that with this storage capacity distributed over a building be suitable for the operating the grid and the production asset. So we'll continue to work on that. Also exchange with several partner and technology providers to test their technology, either on the continental area, European continental, or also in remote Iceland, where we have a specific constraint with grid being much less stable, I would say. Also integrating this intermittent and renewable energy is critical for us if we want to meet the objective that we have nationally, I would say, for each country in Europe.
Thanks, Gilles. I think that's a good remark for the summary of our workshop. So I will give my word back to Susanna. Thank
you very much. Thank you, Pavel, for leading the discussion. Thank you to all who shared their input in the discussion. I would like to thank BuildUp for co-organizing our event, of course to HiBuild for joining us and sharing their results and input. Of course, the project is still running for 1.5 more months, so there are still more things to come. We have a policy workshop planned, we have the training activities, and of course the final results will be shared with all of you. This event was recorded, so feel free to share it with anyone who might be interested. It will be available on the SCORES project YouTube channel, of course linked on the website and posted on all our profiles. Thank you very much for your attention. Thank you to all the speakers who joined us today, and have a nice rest of the day. Goodbye.
Goodbye.